Howdy, folks. We're going to cover the work problems at the end of chapter 6. We're starting with number 3. And it says, how much money needs to be invested now to obtain $2,000 in 3 years if the interest rate is 0.25% and it's compounded continuously? That was the most important part. It said compounded continuously. So right away, we know that we're using the formula A equals PE to the RT. All right, so we choose our formula based on that. And next, we want to diagram our variables. We have A, P, R, and T. So let's reread the problem and fill in what we know. How much money needs to be invested now? That's P. That's our question. We don't know. In order to obtain $2,000, so that's the amount you want at the end. In 3 years, so T equals 3, and the interest rate is 0.25%. So again, we have to move the decimal twice. To the left, that's 0.0025. All right, so you can see what we're looking for. We're trying to solve for P. So we plug all the information in that we currently have into the formula A equals P-E-R-T. So we'd have, let me write the formula again, A equals P-E to the R-T. I plug in A is 2,000. I don't know P, so I just leave P. And then I write E to the R, which is 0.0025. And then T, which is 3. And at this point, I have a number for everything except for P. So I'm just going to calculate E to the 0.0025 times 3. Be very careful with your parentheses. That has to be E to the power of parenthesis 0.0025 times 3, close parenthesis. So now I have 2,000 equals P times 1.0075. I'm just going to write down 4 digits, but I have them all on my calculator. I divide both sides by 1.0075 because I'm trying to solve for P. And my final answer will be P is equal to 2,000 divided by the number that's still on my calculator. So 2,000 divided by second answer, 1985, and 0.06 cents. So $1,985.06 needs to be invested now in order to obtain $2,000 in 3 years at an interest rate of 0.25%. Okay, number 4, interesting problem, multiple parts. It says on May 31st, 2009, almost 10 years ago, the annual percent rate listed Jeff, his bank account for regular savings, was 0.25% compounded monthly. So the key here is saying compounded monthly. That lets us know what formula to use. We are going to use A equals P, 1 plus R over N to the NT. All right? Thank you, guys. Yeah, that's a little better. So again, let's diagram what we know. So we have A, P, R, N, and T. So let's start at the beginning. It's 0.25%, so that's 0.0025 after you move the decimal twice. It's compounded monthly, so N equals 12. And that's actually all we know so far. This is his bank account. So we're going to start with part A. In part A, the question says, if P equals 2,000, so I'm going to write in 2,000, what is A of 8? Now remember, you can write this in function notation. And so the expression A of 8 means if you input 8, what do you get from the function? The input variable is time. So we're saying 8 is 8 years from now, so T equals 8. And you'll notice we've now written down everything except for A. And that's what this function notation is asking. If you plug in 8 for 8 years, what amount of money will you have? So we're about to solve for A. And honestly, in this problem, all we do is plug everything in and calculate it. So A of 8 is simply P, which is 2,000, 1 plus 0.0025 over N. Is that getting right into that bright spot? Let me fix that. Over 12 to the 12 times A. How am I going to get rid of that bright spot? Can I put it this way? It's a little better. Actually, yeah, that's a lot better. Okay, so then from here, I can type all this into my calculator. Remember, you want to calculate the inside of the parentheses separately. So that's 1 plus 0.0025 divided by 12. That's 1.000283 repeating, all to the power of 12 times 8, which is 96. And so I just compute that now. So 2,000 times 1.00208333333333 to the power of 96. And I find that A of 8 is equal to $2,040.40 after you round. It was 0.398, big round. Okay, so if P equals 2,000, what is A of 8? A of 8 means 8 years later, how much do I have? $2,040.40. 8 years is a long time to wait to get $40.40. Okay, next it says solve the equation A of t equals 4,000. So I'm going to erase this because you can just hit rewind and look at it again. So now I want to solve the equation A of t. So again, what is A of t? A of t is the actual formula itself, right? A of t, this is a function in terms of time, is equal to p times 1 plus r over n to the nt. So I'd like to set that equation equal to 4,000. That means the amount at the end is 4,000. So if the amount at the end is 4,000, let me go back here, because now we don't know time. Right, yeah, we want to solve for time. I think we're assuming that we're still using the $2,000 investment, and we're wondering the amount at the end is going to be 4,000. Right, so now we're solving for time. You'll notice I don't know what time is. I do know the amount at the end should be 4,000. We're still investing 2,000. The rate is still 0.0025, and the compounding is still monthly, so n is 12. Okay, so A becomes 4,000, and P is 2,000. And we have 1 plus 0.0025 over 12, all to the power of 12t. Now you'll notice, the only variable left in the equation is t, which is in the exponent, which means we have to solve using a logarithm. So we're going to simplify the inside. I still know what that is. That was that terrible long number, 1.00020833, repeating, all raised to the power of 12t. And that's my exponential expression that I want to isolate. So I'll start by dividing off the 2,000. I divide off 2,000. That's simply 2, which technically means I'm trying to double my money. That's what we're asking. And it's being raised to the power of 12t. Right? So I need to do a logarithm, and then I can solve for t. So what we're looking at here is log base 1.0002. I'm just going to write 1.002 of 2 equals 12t. So let's shift up here real quick. Log base 1.002 of 2. I'll do the change of base. So that's really log 2 over log 1.000208. Repeating. And then that's equal to 12t, but I'm going to divide off the 12 by multiplying by 1/12 on both sides. And therefore, the 1/12 multiplied by this fraction, I put a 12 in the denominator. So that's equal to t. That's how long I have to wait. So let me calculate that. That's log of 2 divided by 12 of log 1.0002083333. And I get t equals 277.29 years. 277 years. That's a long time to wait to double your money. Now, why did it take so long? Because this is such a terrible interest rate. The interest rate is 0.1%. It's like nothing. So 277 years, long time to wait for $2,000. All right, the last question said, what principal P should be invested so the account balance is 2,000 3 years from now? That's the same question as the one we did up above. You know, what principal? Solve for the principal. So I'm just going to set up the equation. What principal should I set up? That means that we don't know the principal. What principal should I invest so that the account balance will be 2,000? So I want 2,000 at the end. But we keep the 0.0025 interest rate, we keep the 12 compoundings, and we know now that we're saying it's 3 years from now. So now we have all the information except for P. So we would plug all that in. Again, I'm just going to set it up for you. This would be A equals P 1 plus R over N to the NT. And we know that the amount is 2,000. We don't know P, that's what we're trying to solve for. And then it'd be 1 plus 0.0025 over 12 to the 12 times 3. And so now you have all the numbers there. That's 2,000 equals P times 1.002083, repeating, all to the power of 36. Okay, I'm so close to finishing the problem. I'll just finish the problem. Then we raise 1.0020833333 to the power of 36. And that gives us 2,000 equals P times 1.0075. There are more decimals, but I'm just writing that. And then I divide both sides by 1.0075. And the principal turns out to be, I'm going to do it using all the decimals on my calculator, 1985 and 6 cents. Wow, that's awfully similar to the answer we got above. Why would it be so similar? It's because it was the same numbers. Hey, it's a pretty good reason to get the same answer is if you were using all the same numbers. That's pretty funny. I said this problem was similar to the one above. It was actually identical to the one above. All right, so that's it for the investment problems. So the next type of problems are about natural growth and natural decay. Natural growth would be growth of populations like human populations, bacteria populations, wolf populations. And natural decay would be like the decay of radioactive materials. In both cases, you notice I'm using the word natural, and that's why we call it the natural logarithm. Because the natural logarithm is used to solve problems in natural growth situations where the letter E pops up quite naturally. So the first thing we want to notice is that they give us a formula for growth, and that formula is n of t equals n sub 0 e to the kt. Now look at this formula real quick. N is referring to the number of individuals in the population. T is referring to time. N sub 0, which British, we call it n naught instead of n sub 0. I might say both ways. E is our number 2.71. K is a constant that represents the type of population. Because as we know, some populations grow quickly and some grow slowly. Bacteria populations grow very quickly, whereas populations of, say, elephants grow pretty slowly because they only have one baby elephant every couple of years, whereas bacteria, they're reproducing all the time. Okay, finally, T is time. So let's take a look here. We're going to do problems A, B, C. The first thing we do is find K. So we're going to find the growth constant for the organism that we're looking at. And since K is in the exponent, we would need to use a logarithm to solve for K. And then part B, just write down the function. So we're just going to write down the function, n of t, once we solve for all the information. And then finally, we're asking the question, how long until there are 9,000 bacteria? So how long until 9,000? Okay. We're doing problem number 5 here. So let's look. It says, under optimal conditions, the growth of a certain strain of E. coli bacteria is modeled by the law of uninhibited growth. So that's what that means. Uninhibited growth means that you can just keep eating as much food as you like and procreating as much as you like and having as many offspring as you like. That's uninhibited growth. So n sub 0 is the initial number of bacteria. That's how many you have in the beginning. T is how much time has gone by. And what they're telling us is, from numerous experiments, it has been determined that the doubling time of the organism is 20 minutes. Let's write that down. Doubling time is 20 minutes. We'll need to figure out how to use that information. Doubling time is 20 minutes. So what does that mean? That means if we plug in 20 minutes for T, whatever population you started with, you should have twice as much. What else do we know? Suppose 1,000 bacteria are present initially. So let's go ahead and diagram. We have the amount at the end, n of t. We have n naught, which is the initial amount, which is 1,000. We have k, which is our growth constant. We don't know that yet. And we have t. All right, so the first thing they'd like us to figure out is k. That was part A, so just find the value for k. Well, the only thing we know is the initial population, which is 1,000. We're solving for k, so that means we need to somehow know what t and the amount is in order to have enough information to solve for k. Well, fortunately, they told us that after 20 minutes goes by, so that's t equals 20, the amount that you have should be twice as much. And since we started with 1,000, after 20 minutes, we will have 2,000. So now I have 3 of the 4 pieces of information, and I can solve for k. So let's jot this down. The formula would be n equals n naught e to the kt. And my final amount will be 2,000. My initial amount is 1,000. E to the k, which I don't know, but t is 20 minutes. Well, by the way, notice that in this problem, time is in minutes, not in years. Okay, so we need to solve for k. It's in the exponent. This is our exponential. We want to isolate it, so we're going to divide off the 1,000. You'll notice that once again, this is 2 equals e to the 20k. So this 2 represents the fact that we're doubling the population size. So now I just convert this from exponential form to log form. I'm going to rewrite it as e to the 20k on the left equals 2. So this is log base e of 2 equals 20k. Log base e of 2 equals 20k. Log base E by definition is really natural log, so that's natural log 2 equals 20k. And k is being multiplied by 20, so I divide by 20, and that gives me my k value. So k equals natural log 2 divided by 20. Very careful with your parentheses. It has to be natural log 2, close your parenthesis, divide by 20, which is 0.0347. It says to round to 4 decimal places. Yeah, round your answer to 4 decimal places. Okay, so now I know my k value is 0.0347. Okay, now if you need to see that again, go ahead and just rewind, and I'm going to erase this now. Part B. Part B says just write the function. Well, that's easy enough. I now know everything about this function. So the function n of t is equal to the initial population n sub 0 is 1,000, and e is just the number e. K is 0.0347, and t is just our variable. So there we go. That's our function. Oh, I'm so sad about that bright light. There we go. Yeah, there's our function. You can see it. All right, so that was part B. And then finally, part C, how long until there are 9,000 bacteria? So the 9,000 bacteria would be the amount at the end. So we should have 9,000 at the end. And they're asking the question, how long? So we don't know how much time. So this is the data we have. We're wanting 9,000 population at the end. We start with 1,000. The k value we know, and t is what we're solving for. So we're going to plug in everything and solve for t. And again, t is in the exponent, so we'll need a logarithm to solve for it. So I plug in the 9,000 for the amount. 9,000 equals 1,000. E to the 0.0347t. And you'll notice the solution is almost identical to the one we just did, solving for k. So we need to isolate the exponential, which means we divide off the 1,000. And then this time what we have is 9,000 divided by 1,000 is 9. So what does that mean we're looking for in our population? We're looking to non-nuple the population, not double, triple, quadruple, quintuple, sextuple, septuple, octuple, but non-nuple or non-nuple. I don't know how to pronounce it. Anyway, we have e to the 0.0347t equals 9. So switching from exponential form into log form, we have log base e of 9 equals 0.0347t. So log base e is really natural log of 9. And then I just divide off the 0.0347 from the t. And we have our answer. So natural log of 9 divided by 0.0347. That's how long the time is. So let's type that in. How long until our population non-nuples? Natural log of 9, close the parenthesis, divide by 0.0347. And I got 63 years. No, sorry. This problem is not in years. This problem is in minutes. So 63 minutes. It only took just over an hour for this population of bacteria to grow 9 times in size. That's pretty unfortunate if the bacteria are inside your stomach. Doesn't take long to get sick. Okay. Well, there we have it. That is a growth problem. And let's just take a look here at the next one. I think it's pretty similar, if not the same. It says here the law of uninhibited growth applies to situations where an animal is reintroduced into a suitable environment. Such a case is the reintroduction of wolves into Yellowstone National Park. According to the National Park Service, the wolf population in Yellowstone was only 52 wolves in 1996 and 118 in 1999. Okay. Use t equals 0 to represent the year 1996. I'm going to go ahead and start a graph. And round your value for k to 4 decimal places. And then finally, according to the model, how many wolves were in Yellowstone in 2002? So first, let's take a look at what we know. We're saying that time equals 0. So this is time. I'll just drop it down a little lower. There we go. Time. And times 0, how many wolves were there? T equals 0 represents the year 1996, and in 1996 there were 52 wolves, so that's your starting population. And then it said in 1999, so that's 1, 2, 3 years later, that's 1999, if time equals 0 is 1996. There we go. Then 3 years later, the population was 118. So there's our next data point. And this represents the exponential growth curve that we're looking at. What else do we need to know? Well, that's all we know. Later on, they say how many wolves were in Yellowstone in 2002. So that's 99. Year 2000, 2001, 2002, which is technically the number 3, 4, 5, 6. So later on, we're interested in a t-value of 6, which is the year 2002. Okay, so let's start by writing down our formula. That's always a good plan, is to write down the formula. So the number of wolves, N of t, is given by the initial population of wolves, and times e to the kt. So the initial population of wolves we already know, because they're telling us that time equals 0 is the initial amount, and in 1996 there were 52 wolves. So we can go ahead and write down my N of t, my N naught, or N sub 0, k, and t. I now know that my initial population was 52. Okay? Then what? They say, find a function which models the number of wolves. So the only thing else that we need to solve for is k. Because you just need to know the initial population. E is just a number. K we need to find. And t is whatever input you want to input into the function. So let's solve for k. We have to plug in information that we do know in order to solve for k. And we can use the coordinate they gave us. This coordinate, 3, 118. That's a coordinate that's for input-output numbers. 3 years after 1996, there were 118 wolves. So if I input 3 into the function, it should equal 118. So watch. I'll start by writing down what I know about the function. N of t is the initial amount, 52, and then e to the kt. And what I know is that if I plug 3 into the function as my input, so that's 52 e to the k times 3, the output should be 118. So this gives me an equation that I can solve in order to solve for k. Because you'll notice I only have one unknown now. So I want to solve that equation. I have my exponential here. I want to isolate my exponential, so I'll divide off the 52. So I divide off the 52. That gives me e to the 3k equals 118 divided by 52, which is 2.26923. There are more decimals, but I'm going to keep them on my calculator. This is a simple exponential. It's base e, so I'm going to say log base e of 2.26. Again, I'm keeping all my decimals on my calculator, equals 3k. And log base e is really just the ln button, so that's natural log of 2.26 equals 3k. And I want to solve for k, so I divide both sides by 3. And my value for k is natural log of 2.26923, etc., divided by 3. So I'll type that into my calculator. And I get a value for k of 0.2731. They said to round to 4 decimal places, so there it is, 0.2731. I'm going to go back to my data. My k value is now 0.273. Now I'm ready to write down my function, right? Just my general function. So again, I'm going to erase because I know you can just erase. I mean, go back and rewind. So now my function is n of t. Let me use a different marker. N of t equals my initial amount of 52, e to the k value, 0.2731 t. All right. So that's my function. What do they want to know? The last question is, according to the model, how many wolves were in Yellowstone in 2002? Well, 2002 is 6 years after the initial amount, so therefore t equals 6. And I want to know if I input 6 for time, how many wolves will there be? So all we do is we just plug in 6. So the number of wolves after 6 years is 52 e to the 0.2731 times 6. So there's no logarithm necessary. We just evaluate all of that. So I'll type 52 e to the parenthesis 0.2731 times 6, close my parenthesis, and the answer is 267 wolves. Well, it's really 267.7 wolves, but we can't have 0.7 of a wolf, so I'm going to round down to 267. Now, they said the actual number was 272. So the model said 267, but the actual number was 272. So is that close? Yeah, it's pretty close, right? I mean, just in terms of a model predicting how many wolves there would be, they got to within 5 wolves. That's not terrible. Okay. Those were both growth problems. And as growth problems, you will notice that both of the K values that we found were positive. So in growth situations, K is greater than 0. K is a positive number. For the bacteria, it was 0.05 something, and for the wolves, it was 0.27 something. So when you have growth, the K value is positive. When you have decay, which we're about to do, the K value is negative. So we should expect that now. As we switch to look at decay problems, these are radioactive decay problems. When we solve for K, we'll expect to find K is a negative number. Now, what are we talking about here? We're talking about the radioactive decay of a radioactive substance. So if you just wanted to imagine that you have some rock of radioactive substance, we measure radioactivity by thinking about half-lives. So let's say that the half-life is 1,000,000 years. Then after 1,000,000 years, half of that substance would no longer be radioactive. After another so this is no longer radioactive. After another 1,000,000 years, half of that will no longer be radioactive. And then after another 1,000,000 years, half of that will no longer be radioactive. And that's how half-lives work with radioactive substances. We measure them in half-lives. So let's take a look at this first problem. Now, once again, our formula is simply A of t. You'll notice it's the exact same formula. A of t equals A sub 0 e to the kt. Same formula. So the amount of radioactive substance you have is a function of time, which is now back into years, where A sub 0 is the initial amount of radioactive substance you have. K is the constant for that particular radioactive substance, because some radioactive substances have short half-lives, like in minutes or even seconds, and some radioactive substances have half-lives in billions of years. So let's go ahead and take a look at our first question. They are describing, so they're saying for each problem, solve for K. We can do that. So part A, solve for K. And then it says find the function, so just write the function down using the K value that we found. And then finally in part C, determine how long it takes for 90% of the material to decay. So let's just think about that. If 90% of the material is gone, how much do we actually still have? If 90% is not radioactive anymore, what percent is still radioactive? 10%. So that's what we're saying. And the last problem we're saying, when will the amount be 10% of what we started with? Okay, let's go ahead and try it out. Let's turn the screen, look at the first problem here. It says, not this problem, I'm actually doing that problem up there. Should I stand on a chair? I'll stand on a chair. Okay, cobalt-60. Used in food irradiation, you have an initial amount of 50 grams. So let me start by writing out my function. A of t equals A sub 0 e to the kt. So let me diagram here. I've got A of t, which is the amount, A sub 0, which is the initial amount, K is a constant for that element, and T is time. So they're telling us we have an initial amount of 50 grams, and the half-life is 5.27 years. Now we can't just write that in anywhere. We're going to use that fact to solve for K. So what does that mean that the half-life is 5.27 years? That means that if I plug in 5.27 years, then the amount that I'll have is half of what I started with. Okay? So let's write that as a coordinate. If I plug in 5.27 years, then how much will I have? Half of 50 grams, which is 25 grams. So what they're telling us is input-output. If I input 5.27 years, the output should be 25 grams. So let's do that. If I input a time of 5.27, the amount at the end is 25, and we now have 3 pieces of data, and we're only missing our K value, so we can solve for K. So let's plug all this into our formula. So that would be, I'm going to write it right above it so you can see it. So the amount at the end is 25 grams. The amount at the beginning was 50 grams. The K value we don't know, but time is 5.27. Right? So remember, anytime you solve any equation, you need to plug in enough information so you only have one variable left, because you can only ever solve for one variable. So I want to isolate my exponential. It's being multiplied by 50. I divide by 50. And this time you'll notice 25 divided by 50 is 1/2. I'm going to write 0.5. But it's 1/2 because it's a half-life. We're wanting half of the substance to still be there. Now this is e to the 5.27k. So I'm going to turn that into a logarithm. So this would be log base e of 0.5 equals 5.27k. So log base e, recall, is just ln. ln of 0.5 equals 5.27k. So k is being multiplied by 5.27. I divide by 5.27, and that is going to be our answer for k. So k is equal to natural log of 0.5 divided by 5.27, and it's negative 0.1315. Remember, we're expecting a negative k value because this is a decay situation. All right, so k is negative 0.1315. Okay, there we go, we solved for k. The next thing we would do is just write down our function. So now, again, if you write the function blank first, a of t equals a sub naught e to the kt. Plug in what we know. This function, the amount of substance as a function of time, is the original 50 grams e to the negative 0.1315 t. Okay, so that was part B, just write down the function. The last question is, how long do you have to wait? So we're solving for time. And where's time? In the exponent, so we'll need a logarithm. How long do you have to wait for 10% of the substance to remain? Well, what's 10% of 50 grams? 10% of 50 grams, you do 0.10 times 50. And that means only 5 grams remain. So I want only 5 grams to remain, starting with 50, and it's e to the negative 0.1315 t. So we just do a logarithm to solve for t. Our exponential is being multiplied by 50, so we divide by 50. And notice here you get 1/10 or 0.1 because we're saying when until only 10% remains. The question was 90% is gone, which means 10% remains. So 0.1 equals e to the negative 0.1315 t. Convert from exponential form to log form. So log base e of 0.1 equals negative 0.1315 t. Log base e is really natural log, so natural log of 0.1 equals negative 0.1315 t. T is being multiplied by negative 0.1315, so I divide by negative 0.1315. And I get my value for t, which is natural log of 0.1 divided by negative 0.1315. And that's 17.51 years. That particular question was talking about years. Yeah, there we go. All right. Well, the next problem is just like it. So we don't have to do it. You can cross it out. And I believe that's it. Please email me with your questions. You can always hit rewind, watch that again, but email me with your questions. I'd be happy to help. Your test is on Monday. And like I said, these questions about radioactivity, those are bonus. Those are extra credit.